All right. Well, welcome back, folks. Hopefully, you had a chance to take a look at the material yesterday, and hopefully you understand it. I think it's pretty straightforward. I haven't seen anybody in a while, so what I think I'm going to try to do is next week. I'll let you know. But I would like to arrange a time that we can have a live Zoom meeting, and that way then we can kind of just get caught up, see each other face to face, and see how things are going. And so I'll let you know. I'll update you. I'll let you know if we can get that done and when we'll get that done. Okay. But in the meantime, like I said, office hours 1:30 to 2:30. Make sure you come by and get your questions answered. Those will be live. Those will always be live. And then I'll answer your questions then. Okay? All right. Let's go ahead then. And what I'd like to do is I'm going to start out with this problem here. This problem here is going to ask you to, and you take a look at it, it's going to ask you to, first of all, balance the equation. So this is an equation here. Always check when you were given an equation. Always check to make sure that it's balanced, because from that balanced equation, we can obtain information about the relative amounts of the reactants and the products. We can use that then to help us carry out the reaction we need to. And so essentially what I'm asking you to do here, number 7, is apply what we've learned up to this point. This is a problem that we can use to review everything we've talked about up to this point. So as when we go over this problem here, if there's any point in the discussion that you don't quite understand, again, make sure you come by and see me. Just one last note before we get started here. There's still a couple of you, 2 of you here, and I will send out an email again to the 2 of you. You need to make sure you take that exam, folks. And as soon as I have them finish taking their exams, I'll send out the results for you. Okay. But I'll contact you folks, the 2 of you, or you can come by or you can email me and arrange a time where you can take the makeup exam, but please make sure you get that done. Okay. All right. So with that said, then let's go ahead. Let's work out this problem here and then take about 3 minutes or so. Within those 3 minutes, try to do as much as you can. And then what we'll do is we'll come back together and then I'll go over this problem with you. Okay, so take about 3 minutes, do as much of it as you can. And then when we get back, we'll go over this problem together. Make sure you write down the work that we do together in lecture here, and then compare that to what you did, and then make sure at the end of the period you submit your work and the work that we did together. Okay, all right, take about 3 minutes, get this problem done. Okay, let's go ahead then and let's take a look at what we have here. Let me go ahead and scroll down. Okay, all right. So this is the equation that we are asked. This is the reaction that we were asked to examine. Okay, so this is the reaction that we're asked to take a look at and do. And so the very first thing you want to make sure you do is you want to make sure you balance out the equation. Now, if you did not get the balanced equation here, which would be 2, 5, 4, and 2. If you did not get that, folks, if you did not get these coefficients here, if you did not get these numbers, please come by and see me. You absolutely need to be able to balance out the equations here. And hopefully you recognize that this is a combustion reaction from chapter 11. And so this is how you balance out the combustion reaction here with these coefficients here, okay? All right, so I'm not going to, hopefully you can recognize here, so on the atomic scale here, that means that we interpret this equation on the atomic scale. I'm not gonna count all the atoms for you. You make sure you do that, but hopefully you recognize then that and the problem didn't ask you to do this, but I'm gonna do this just really quickly. On the atomic scale here, you're gonna notice then that we'll start out with 18 atoms, 18 total atoms, okay? And we should end up with 18 total atoms as well. Okay. All right. So atoms are conserved here, so make sure you keep that in mind. So that we can count atoms. Make sure what we're doing is we're counting individual atoms here. And so you notice here we have 4 carbon atoms here, which matches the 4 carbon atoms on this side. But the total number of atoms have to be the same on both sides. Okay. So make sure you can get that. If you did not get that, make sure you come by and see me. Okay. All right. So on the next level up, let's go ahead and take a look at the molecular level, the molecules. Okay, and again, when we count molecules here, we're counting total molecules. We have then 7 total molecules on the left. Remember, the coefficient here gives us the total number of molecules. So we have 7 molecules on the left. And again, make sure you recognize then to give us then 6 total molecules on the right. Okay, so we start out with 2 ethanes, 2 of the C2H2s, 5 of the O2s, we end up with 4 CO2s and 2 H2Os, and that's how we get these numbers here. Okay, so make sure you're able to do that as well. Okay. All right, so with that said, what I want to do then is let's start with the molar level here. Okay, so what we have here then is we're told then that, I'm sorry, we will have to start out with then 2 moles from the coefficient here, 2 moles of C2H2. Okay, and on the reactant side again, we'll have 5 moles of O2 to produce then 4 moles of CO2 and 2 moles of H2O, which gives us then a total of 7 moles, okay, and to start out with, and a total of 6 moles end up with. And if you notice then, the numbers here for moles and molecules are the same, but again, remember, we are scaling it up. Here we're dealing with 7 individual molecules, okay, 2 of these and 5 of these, okay, and here we're dealing with 6 total individual molecules, 4 and 6. Remember, when we deal with moles here, we're dealing with Avogadro's number. So we have twice as many, Avogadro's number here, 5 times Avogadro's number here, 4 times Avogadro's number here, and 2 times Avogadro's number here, which means that we've scaled up the amount of particles by a bit, quite a bit. Okay. All right. So with that said, then this doesn't really help us. Okay. So what we have to do then is we're going to calculate for the masses. Okay. So let's go ahead, and this will be our first math calculation here. For the first 3 levels here, we're just counting. Okay. We don't have to worry about calculating anything here. We just make sure we count using the coefficients, okay? So for the first 3, we don't have to do any calculations, but starting with masses here, we actually have to calculate for it, okay? So let's go ahead and let's do the calculation, okay? So let's start out that we want to find the mass of C2H2. So we know then that we have 2 moles of C2H2, and we want to find then the mass of C2H2. We have to find then the molar mass. We're going to plug that in, and then molar mass here is going to be 2 carbons, 2 hydrogens. It's going to be 26 grams of C2H2 over 1 mole of C2H2. And then we end up then here with 52 grams of C2H2. Okay, let's go ahead and do the same thing for the remaining 3. Okay, so we have then 5 moles of O2. We're going to find the mass then of O2. Molar mass then of O2, oxygen then is going to be 32 grams for every 1 mole of O2, which gives us then here 160 grams of O2. Let's go ahead and do the same thing then for carbon dioxide. We have 4 moles, okay, of CO2. We want grams of CO2. The molar mass of carbon dioxide is 44 grams per mole for every 1 mole CO2. We end up here with 176 grams of CO2. And then finally, for H2O, we have 2 moles of H2O. We're going to find then the grams of H2O. So we're going to multiply by 8 molar mass of water, which is 18 grams for every 1 mole. Okay. We end up here then with 36 grams of water. Okay. All right. So with that said, then make sure you understand then these are the masses that we start out with. These are the masses of the reactants. These are the masses of the products. And if you notice here, if you add these 2 up here, we end up with a total of 212 grams to start out with. If you add these 2 up here, you're going to notice then that we also get 212 grams to end up with. And so we have conservation of mass here. So mass is conserved. We're going to talk about that today a little bit more, hopefully, in just a moment towards the end of the period. But make sure you understand then that the masses have to be equal. If these masses are not the same at the end of the process, you did something wrong here. Okay. So make sure you're able to calculate for these masses here and be able to get that done. Okay. All right, so with that said, then let me go ahead and let me clear this up so I can do the next part again. Okay, so do the last one. Okay, so we have here then 2, let me go ahead and fill it in again, 2, 5, 4, and 2. Okay, so now we want to find the volumes. Okay, so now the last part of this question is they want us to find the volumes. Okay, all right. So with that said, then if we know the moles, and so here again, remember we can only do this if we have gases and if the gases are at STP. Okay, so we can do this conversion here if that is true. So if we start out with 2 moles of this gas here with C2H2, if the gas is if all these gases are STP, so C2H2 is a gas, oxygen's a gas, carbon dioxide, CO2 is a gas, and here it's water vapor, so water is a gas. We can go ahead and convert that into volume using the molar volume. And the molar volume will always be the same, which is going to be then 22.4 liters of in this case, C2H2 over 1 mole of C2H2. So therefore, this is going to be equivalent to 44.8 liters. Let's go and do the same thing for the remaining substances, the remaining components of this reaction. Starting with oxygen, then we have 5 moles of O2. Remember, we're not using the molar mass here because this is a volume that we want. So again, here we will use the same 22.4 liters of O2 over 1 mole of O2. And so therefore we have here 112 liters of oxygen. Okay. And we have then 4 moles of CO2. Okay. And we want to convert that to liters of CO2. And again, since this is a gas at STP, we will use 22.4 liters of CO2 over 1 mole of CO2. And we end up here with 89.6 liters. And then finally for the water, then we have 2 moles of water. We want the volume of water. And again, we're going to use 22.4 liters of H2O over 1 mole of H2O. We end up here with 44.8 liters. Okay. All right. So with that said, then this is from chapter 10. Make sure you remember. Make sure you remember that. If not, then again, look back into chapter 10, and if you need to, come by and see me. But if you notice here, the molar volume that we've used is exactly the same for every single one of these calculations. Why? Because the identity of the gas doesn't matter. Remember, the identity of the gas doesn't matter as long as you have 1 mole of that particular gas. Okay. And if the gas is at STP, then they will always occupy the same volume. And so if we have different moles here, if we have different amounts in terms of moles, we can figure out then what the volumes are for each one of these. Okay? And so if you notice here, if you take and you add up the volumes of the reactants and the volumes of the products, they do not equal one another. Okay? They do not equal one another, and we don't expect them to do that. Okay? Because when we talk about conservation, conservation only applies to masses and to atoms. Okay? It doesn't apply to volumes. Okay? All right. So make sure you understand that what we're saying here is that if we start out with 44.8 liters of ethene, which is C2H2, and we react it with 112 liters of oxygen, we will produce 89.6 liters of carbon dioxide and 44.8 liters of water. Okay? And so we obtained all of these volumes. So we obtained all of the masses from this balanced equation here. So you had to balance it first. Okay? So with the volumes and with the masses, we don't get it directly. We have to calculate. We have to do our calculation in order to get the amounts there, but we can get the calculation is a fairly straightforward, simple one. Okay. All right, very good. So that's what we went over. That's what we've done up until this point. And so make sure you review that and make sure you get that done. The homework for tonight is going to ask you to set B from chapter 12. Is going to ask you to do this these types of problems here. Make sure you practice that as well. Okay. All right, so let's quickly discuss that in conservation, and then we'll do a few more of these practice problems here. Remember, mass and atoms. So when we talk about conservation, when we talk about what is being conserved in when we do these problems here. It's going to be mass and the atoms that are always conserved, meaning then the masses have to be the same on both sides when we finish calculating. Remember, this is calculation, so we have to calculate for this. At the end of the calculation, when we calculate, at the end of the calculation, the masses have to be on the same on both sides. And here we just have to count. Okay, and at the end of our count, the number of atoms should always be the same. So our calculated masses should always end up being the same for both sides of the chemical equation, and our counted quantities of atoms here will always be the same as well. Okay, molecules form the unit of moles. When you do the counting or when you do the calculation, they will not be conserved. Okay, so these values here are not conserved. Okay, they're not always going to be conserved. Now, will you have occasions where you have a specific type of reaction and they end up working out that way? Yes, you'll have that. But remember, it's always going to be then the masses and atoms then that will always be conserved. So make sure you keep that in mind as we move forward here. Okay? All right, so with that said, let's take a look at an example. Let's interpret this equation here. Okay, interpret this equation here, and I want you to take a couple minutes to do this. Okay, so let's go ahead and work out this together. Okay. All right, so let's go ahead and interpret this equation here. First of all, in terms of representative particles and moles. We're not going to count atoms here, okay? So we have then representative particles. Again, this term here we can apply to the word molecules. Okay, so we're going to count total particles here. So we have 2 particles of H2S, dihydrogen sulfide, and 3 particles of O2 to start out with. Okay, we end up with 2 molecules of SO2 and 2 particles of H2O, which means that we have 5 total particles to start out with, and we only have 4 total particles to end up with. Okay, and if you notice then that conservation does not occur here. We have 5, we start out 5, we only end up with 4, which is fine because these are particles. Okay? All right, so with that said then, let's quickly do moles as well. So this is molecules, let's do moles, and then I'll clear the screen and we'll do masses. Okay, so here then we have 2 moles. So not just 2 individual particles of H2O, we now have 2 moles of H2O, H2S, which is then, remember, twice Avogadro's number. So we take Avogadro's number, which is 6.02 times 10 to the 23rd, okay, and we double it. And that's how many we have here with 2 moles. Okay? So with that said, then we have 3 moles of oxygen, okay, to produce then 2 moles of sulfur dioxide and 2 moles of water. Okay, and if you notice here, total moles, you add it up, we have 5 moles of 5 total moles. Okay, and here then we have 4. I'm sorry, let me say total here to make sure you're clear on this. Okay, so we have then 5 total moles on the left and 4 total moles on the right. And if you notice, then the number of moles will not equal one another. Okay. All right. Make sure you write that down. And what I'd like you to do now then is real quick, I'd like you to calculate for the masses here. So calculate for the masses of each one of these. So what I'd like you to do, write this down and show me your work, calculate the masses. And then when we come back, I will calculate these out. I will work these out for you. And then we'll compare masses. Okay, so take about 3 minutes, calculate for the masses. This is more practice for you in doing these conversions. So calculate for the masses here, and then when you get back, we will take a look at them. Okay. All right, let's go ahead and let's do the masses. Okay, so for the first one, then we're going to do 2 moles of H2S. Make sure you understand where this number comes from. It comes from right here. We're going to convert this into grams of H2S, which means then we're the mass here is going to be 34.1 molar mass, grams H2S, 1 mole H2S, and this gives us a mass of 68.2 grams, and because I didn't round here, okay. All right, so we have then 3 moles of O2. Okay, we're going to find mass of O2, and let me just finish up here really quickly. This is going to be 32 grams for every 1 mole of O2. This gives us here then 96 grams of O2. Okay, all right, so those are the reactants. Let's go ahead and calculate for the products. We have 2 moles of SO2. Okay, we will find then the mass of SO2. The molar mass of SO2 is 64.1 grams SO2 for every 1 mole of SO2. This gives us 128.2 grams. And then finally, water, then we have 2 moles of H2O. Okay, we want to find the grams of H2O. Okay, this is going to be 18 grams per mole for every 1 mole of H2O. And so therefore we end up here with 36 grams of water. Okay, all right, so add those two up, okay, and what you're going to get here then is 164.2 total mass on the reactant side. Okay, and if you add these two up here again, we're going to get 164.2 grams total mass on the right. So mass is conserved. Okay, so let's go ahead and emphasize this here. Okay, mass is conserved, and we expect it to be conserved as we do this. Okay, all right. So what I would like you to do to finish out here then, the problem doesn't ask you this, but I want you to calculate for the volumes. Just to finish up here, calculate for the volumes of reactants and products. So you calculate for the volumes on both sides. So, and then I'd like you to submit that work. And what we'll do then is tomorrow, I'll go over this with you, and then you can compare your answers. But for right now, just to finish up then, on your paper, folks, before you submit at the end of the period here, just real quick, calculate for the volumes involved, because these are all gases. Assume STP, calculate for the volumes, and then obtain those volumes, and then tell me whether you volume is conserved or not, and then we'll pick up with this problem, this particular problem tomorrow. So this is an extra problem that I'm asking you to do here at the end of the period. Get this done really quickly. Submit it, and then I will see you folks tomorrow. Or if you're having a hard time doing this problem here, come on by after school today, and I'll work out this problem for you. Okay. All right, folks. So very good. If I don't see you this afternoon, I will see you tomorrow.